Okay, in this tutorial, we'll see how to use R to fit a logistic regression model. So there'll be two parts to this tutorial. Mainly because I'll be showing how to fit a logistic regression model when you have ungrouped versus when you have grouped data. So the first example will be with what I call ungrouped data. So the data set is data on some of the passengers on the Titanic ship that sank in 1912. So let's read that in. And always one of the first things I say, right, that I like to do is just see how the data are recorded. So we have 707 data points, and the variables of interest that they recorded data on are whether the passenger survived or not, 0 for did not survive and 1 for survived, the gender of the passenger, the age of the passenger, as well as the fare paid by the passenger. So I believe this fare has been adjusted for inflation, and so that's why there are many decimal points over here. So we want to see, right, how these factors affect the survival rate of the passengers. So, and this is called ungrouped data because the data, each line corresponds to each individual, right? The individuals are not grouped into groups with similar characteristics. It tells us for each individual what their values are, what their outcome is. So we're going to fit a logistic regression model where we are going to use the amount of money they paid to see whether we can predict whether that passenger survived or not. For logistic regression, we use what we call a GLM function, which is short for generalized linear model. In this setting, you have to specify the family. So for a logistic regression model, because we model the response using a binomial distribution, we have to put binomial as the family. Truth be told, you could use the GLM function for your linear regression model as well. You'll be putting the Gaussian, the word Gaussian for family. So Gaussian is another word for normal distribution. The one difference is that GLM uses maximum likelihood estimation, whereas the LM function that we've been using uses least squares to estimate the regression coefficient. So let me just fit this model, and let's just look at use the summary function of our GLM model. And a lot of the information, right, so that's the estimated intercept, estimated slope for the predicted fare, the z statistic, and the p-value. So the main thing for us to look at is, right, we want to see whether the predictor, the amount of money paid, whether that's significant. So this is the wall test with a z statistic of 6.399 and a small p-value. So this tells us that this is indeed significant, right? The amount of money paid is significant. Is a significant predictor for the survival rate of the passengers. If you want to find a confidence interval for the coefficients, right, we can use our usual conf_in function, your LM model, level 0.95, and that will give you the 95 upper and lower bounds of the 95% confidence intervals associated with all your coefficients. The other thing to take note of is that you get the null deviance and the residual deviance given to us. The null deviance basically is the residual sum of squares of the intercept only model. So this is saying, right, if we don't have the amount of money paid, we only consider the intercept, what's the residual sum of squares of that model. So that's the null deviance. This degree of freedom is going to be the sample size minus 1. So we had 707 data points minus 1. The residual deviance is basically the residual sum of squares of our specific model. Degrees of freedom is n minus the number of parameters you have, which is 2, right? Because one intercept and one predictor. So this is analogous to the residual sum of squares for our model. Obviously, the smaller this is, the better. What else could we do? Right, the next thing we could do is to perform a test to see whether whether the coefficients are 0 or not. So the next thing I'm going to do is to consider fitting a full model with all 3 predictors. So I'm going to call this model full. Run that again. Use the summary function for that model. Right, we can kind of see that gender is significant. Age doesn't appear to be significant, right? The residual deviance of this 3 predictor model, notice it goes down, right? So as we add more predictors, residual sum of squares tend to go down. That's 707 minus 4 because we have 1 intercept and 3 predictors. Notice the null deviance stays the same. So as long as your response variable is the same, the null deviance for your model will remain the same regardless of the number of predictors you add in. So the next thing we could do is to say whether all these three coefficients are 0 or whether at least one of these is different from 0, right? So that's like the ANOVA F-test in a linear regression setting, right? Over here we use what we call a delta G-squared test statistic. So the delta G-squared test statistic basically looks at the difference between the residual deviance and the null deviance. The degrees of freedom will be 3 because that's the difference between 706 and 703, and this follows a chi-square distribution. So the test statistic, that's how we get it, right? The null deviance minus the deviance of this model, p chi-square of this test statistic comma 3. And if you had done just p chi-square, that would give you area to the left, but we want area to the right. So we have to subtract this probability from 1. All right, the null hypothesis is saying that all these three coefficients, beta 1, beta 2, beta 3 are 0. Alternative is saying at least one of them is non-zero. Right, small p-value, so we reject the null data supports the claim that at least one of these coefficients is non-zero, which shouldn't be too surprising, right, given the fact that we have two significant predictors here. So that's how we can test, right, the equivalent of the ANOVA F-test, i.e. whether all these three coefficients are 0 or not. Now, if you want to test whether just a subset of these coefficients are 0 or not, right, so as usual, the individual tests only tells us whether that predictor can be removed and whether you leave the other two. But let's say I want to remove the last two, right? So if I want to remove the last two, I might say, well, could I stick with my original model with just the amount of money paid as the only predictor? Or is adding these two predictors worth, right, the extra complexity? So again, we are going to carry out something similar to the partial F-test. We're just going to calculate our delta G-squared test statistic by looking at the difference in the residual deviances between this model and the model with just one predictor. So that's where this comes in. It's basically the difference in the residual deviances between the two models. 2 degrees of freedom because we are looking at an additional 2 predictors, and then we're using the p chi-square function to find the p-value and subtract that from 1. So the null hypothesis is saying that that coefficient and that coefficient, they're both 0. Alternative is saying at least one of these is not 0. Small p-value, we reject the null. So it tells us that at least one of these two coefficients are non-zero, i.e. we should go with the more complicated model because it improves the prediction sufficiently. Right, so that's how we can carry out something analogous to a partial F-test, right, using the delta G-squared test statistic in a logistic regression framework.